Good morning, everyone. My name is Veronica Mattioli, and I'm a PhD student at the University of Parma. Today, I'm going to present you my master thesis work that concerns a maximum likelihood algorithm for speed estimation of foreground objects in video signals. The proposed method is nothing but a video processing solution for motion estimation. This kind of techniques are nowadays widely employed in contexts such as street monitoring and traffic analysis. The issue is that framed objects may experience dynamic changes throughout the video, and these changes may be either due to perspectival effects or periodic behaviors. Our first goal is to estimate the speed of objects framed in simplified scenarios, where all the geometrical transformations can be neglected. Nevertheless, as a further enhancement, we include any dynamic transformation in the analysis. We derive this model to describe a video signal in time domain. X represents the pixel intensities at position M and frame N, and now I'm going to describe each of these terms. The first term is B. It represents the background, which is static, hence only depends on the spatial coordinates M. S of I is the image of the ith object at time index n1, and capital I is the total number of framed objects that we set equal to 1. VB is the term that takes into account the occluded parts of background, which are covered by the moving object, and will be neglected for the sake of simplicity. This new term represents instead the shift in the two-dimensional image plane of the ith object. Delta is the displacement vector, and we assume the speed to be constant. As you can see from this animation, the object has not only shifted, but it has also been subject to a modification from time n1 to time n2. Finally, the last term represents the samples of independent and identically distributed zero-mean Gaussian noise. As I previously mentioned, the model in 1 is written in time domain. Nevertheless, we choose to work in the frequency domain by applying the Fourier transform properties. Following standard techniques of maximum likelihood estimation, we were able to derive this expression as the log likelihood function of the frequency domain model. The results of the maximization process is written immediately after in expression 3, which represents the estimator of the speed vector v. For further simplification, we also apply the background removal technique, namely the Gaussian mixture model, and this allows to neglect all the background-related terms. Here we come to the results. The first example is a real video of a car moving with a horizontal speed of -7.9 pixels per frame. This is the video after the background removal, and on the right side you can see the log likelihood function plotted versus the speed components. The results, namely the estimated speed, is highlighted in the maximum peak in -8,0, which is very close to the correct result. As a second example, here we have a synthetic video, where the moving object is subject to a periodic transformation. As you can see, we superimposed additive white Gaussian noise to the video in order to test the robustness of the proposed method. This is again the video after the background removal, and on the right side you can still see the obtained results. In this case, the estimated speed is highlighted in the maximum peak at 4.2, that exactly corresponds to the correct value. In conclusion, we propose the maximum likelihood speed estimation algorithm for objects framed in video signals, and we analyze the case where geometrical transformations are superimposed to the motion. We were able to validate our theoretical derivations by numerical simulation performed on both synthetic and real videos. Furthermore, we were able to prove the robustness of the proposed method in presence of noise. For further details, you are referred to the two publications cited here that are directly originated from this thesis work. Thank you for your attention.